All right, I'm really trying to get these videos under 7 minutes. I have a tendency, I think, to over-explain things, but I'm trying to make certain that every single step is clear, but I think maybe I'm going to try to minimize that tendency. So, what are we trying to do? We are trying to prove that, or we are trying to find out what are the consequences of assuming that the electric field for a point charge is defined by kq over r squared, r squared in the r hat direction. And yes, that's supposed to be an r. All right. Basically, when I say what are the consequences, what we're trying to say is what does that imply about E dot dA for this integral of flux over a closed surface. Oh, you can't see that with all those plants we have in there. All right, so what do we have? We have some charge Q. And we will recall that dA is, since I've done it with capitals everywhere else, dA equals r squared sine theta d theta d phi in the r hat direction. Excellent, made it. Okay, and what is our E? E is this. So when we want to calculate this E dot dA, we can just plug these in. So I'm going to go ahead and skip down a line so I make sure I have the room to do this. And I'm going to write, I'll write everything in here. KQ over R squared sine theta d phi, and this is r hat dot r hat. In other words, the direction for both of these is r hat, so r hat dot r hat. What's r hat? R hat is a unit vector. Any vector times any vector dotted with itself just gives us the magnitude of that vector, which is 1. So we are going to go ahead and, what, is it the magnitude squared? It might be, but it doesn't matter because this is all 1, so this is just going to give us a factor of 1. So all we are left with here is I'm going to pull out, well, actually, let's do this. R squared cancels R squared. Amazing. So I'm going to end up with KQ, this closed loop integral of sine theta d phi. In an earlier version of this video, I went into great detail about the r dot r, but I'm not going to do that now. And I'm also not going to go into a lot of detail about this, but just to remind you that this integral will be from 0 to pi for theta and 0 to 2 pi for phi. Okay, and this ends up being, as you guys might remember, this ends up being, we have a minus cosine theta, 0 pi, and we have a phi from 0 to 2 pi, and so this, oh, gosh darn it, that's what we have. And there we go. And that's going to give us going to say this equal to KQ times 4 pi K. Oh, excuse me, we already have that. Okay. KQ times 4 pi. All right, and then the question is, what is K? K is Coulomb's constant, which we know is 1 over 4 pi epsilon 0. So if we plug that into there, what we end up with is that the integral of our closed loop of E dot dA is going to equal Q 4 pi over 4 pi epsilon 0. Our 4 pi's cancel, and we have integral around a closed surface of dA equals Q inside divided by epsilon 0. And, oh shoot, once again I'm going off the screen. Okay, so I'm just doing the rewriting there, and the simplest cancellation possible, the 4 pi's cancel. So what is that? That is Gauss's law. So what we have just shown is that if Coulomb's law is true, Gauss's law is true, and if Gauss's law is true, Coulomb's law is true. So what this says is we can replace using Coulomb's law with using Gauss's law when it's more convenient for us to do that. So we are going to find several situations where it's convenient to do that, and we'll talk about that in the next video.